Welcome to Naradar Academy. In this video, we are going to discuss few topics in functional analysis. The first one is norm-linear space. See, norm-linear space is a linear space in which for each vector x, we define norm x, okay, such that it satisfies these conditions. First one is norm of x is always positive. Okay, norm x is always greater than or equal to 0, and norm x is equal to 0 if and only if x is equal to 0. Next one is norm of x plus y is less than or equal to norm x plus norm y. And the third one is norm alpha x is equal to modulus alpha into norm x, where this alpha is the scalar taken from the field. Okay, now linear space is nothing but vector space only. Okay, so we take a vector space and in that one we are defining a norm. Okay, this norm is almost equivalent to the definition of length of a vector. Okay, so this norm we have to define in such a way that it has to satisfy all these three properties. If these three properties are satisfied, that space is called what? Norm linear space with respect to the given norm. So for a given norm linear space or a given linear space, we can define norms in different ways. It need not be a unique. Okay, right? So the thing is, it has to satisfy all these three criteria. Then it is called a norm linear space. Okay. Next one important note is every norm linear space is a metric space. Okay, metric space, and metric space means what? It has to be defined with a metric, isn't it? Metric means what? Distance between the vectors. So in a norm linear space, how will you define the metric? The metric is defined by d of xy is equal to norm of x minus y. Okay, so with respect to this metric, the given norm linear space will become a metric space. So what we conclude here, every norm linear space is a metric space. Okay, let's come back to the norm linear space definition again. See, this norm already you have studied in inner product spaces, isn't it? That is, inner product of a vector x with itself is called norm x square, right? So what is the connection between inner product space and norm linear space? If you are given with an inner product space, definitely it will be a norm linear space, right? Because there you are defining one inner product which will satisfy all the criteria for norm linear space. But when you are given with norm linear space, it need not be a inner product space. Okay, right. Next one, Banach space. Banach space means it is a complete norm linear space. Okay, just a complete norm linear space is called Banach space. Next, what do you mean by a complete? Complete means, suppose if you take any Cauchy sequence from the norm linear space, okay, take a Cauchy sequence. Cauchy sequence means it will be converging, no? It will converge to some point, no? That point must be a element of the norm linear space. Okay, that is, if you take xn is a Cauchy sequence in the norm linear space, xn is a Cauchy sequence in the norm linear space, then xn will be converging to some x, no? That x must also be an element of the norm linear space. Okay, that kind of space is called what? Complete space. And the complete norm linear space, we call it as Banach space. Let's see some results for this norm. The first one is modulus of norm x minus norm y is less than or equal to norm of x minus y. This is similar to modulus x minus y that we define in real numbers. No, modulus x minus y is greater than or equal to modulus of mod x minus mod y. That you remember, this property is similar to that one only. Here what do we say? Norm x minus y is greater than or equal to modulus of norm x minus norm y. So this is similar to the property which we study for real numbers. Okay, right. Next one is norm is a continuous function. Okay, so if you take a norm linear space, we will be providing with one norm, no? That norm is a continuous function. That means what? If you take a sequence xn which is converging to x, then norm xn will be another sequence, no? That sequence will converge to norm x. Okay, this property, what we call norm, is a continuous function. That is, whenever you have a sequence xn converging to x, then norm of the sequence norm xn converges to norm x. Right. Next one. Addition and scalar multiplication are jointly continuous in a nonlinear space. That means if you take two sequences xn and yn be two sequences which are converging to x and y respectively, right, then what is the conclusion we have? The sequence xn plus yn converges to x plus y, and what we say, scalar multiplication means what? Alpha x, alpha n xn converges to alpha x. So addition and scalar multiplication are also jointly continuous in case of nonlinear space. Next one is we are going to define quotient space. This is also similar to the one which you have defined in groups, rings, and so on. For defining the quotient space, first I am taking a closed linear subspace M of a nonlinear space. See, N is a nonlinear space. In that M, what I am taking? I am taking one closed linear subspace M, right? Then I am defining in n by m is called quotient space. In that one, I am defining the norm. How will you write the elements of n by m? X plus m, where x is an element of n and plus m is equal to infimum of norm of x plus m, where m varies over m. With respect to this norm, n by m will become a norm-linear space. Okay, suppose if your n is a Banach space, then n by m is also a Banach space, right? So we have defined what is a quotient space and how do you define the norm in terms of in the quotient space. So this quotient space will also become a nonlinear space. When n is a Banach space, n by m will also become a Banach space. Okay, this is another result. Then the next one is, let's see some basic examples. R and C. R means what? Real numbers. The set of all real numbers and set of all complex numbers are Banach spaces, right? Banach spaces means what? They are nonlinear spaces and they are complete. So how nonlinear space means what? You will be defined with some norm. So how do you define norm in this R and C? That is real numbers and complex numbers. Norm of x is defined as modulus x, our simple modulus function. Okay, so with respect to this norm, they are nonlinear spaces, and already we know that R and C are complete. That means what? If you take a Cauchy sequence in the field of real numbers, that will again converge to a real number, and then if you take a Cauchy sequence of complex numbers, that will again converge to a complex number. So they are complete also. Therefore, what do we conclude? R and C are Banach spaces with respect to the norm defined by norm x is equal to modulus x. Okay, next let's see what about Rn and Cn, n-dimensional spaces. They are also Banach spaces, and these are called Euclidean and unitary space. Okay, these are called what? Rn is called Euclidean space and Cn is called unitary space. And usually the standard norm here is defined to be norm x is equal to summation I equal to 1 to n modulus xi square the whole power half. Okay, that is norm x is equal to square root of x1 square plus x2 square plus x3 square plus etc. xn square. This you can identify with the distance of the vector x from the origin. How will you define distance between any two vectors? Square root of x1 minus y1 the whole square plus x2 minus y2 the whole square plus etc. xn minus yn the whole square. No. So this norm x defined here will give you the length of the vector from the origin. Okay, so with respect to this norm, Rn and Cn are Banach spaces and they are called what? Euclidean and unitary spaces. Okay, this is not the only way for defining norm in Rn and Cn. We have so many different ways. Let's see one by one. Suppose if p is a real number which is greater than 1 and less than infinity, then LPN we are defining the space of n tuples. Same thing like Rn only, x1, x2, etc. xn, n tuples, but here the norm is defined to be norm xp is equal to, okay, pth root of x1 power p plus x2 power p plus etc. xn power p. See, this sometimes we used to write it as norm 2. In the base here, no, you have to put 2. But generally, if you write simply norm, that represents only this norm only. But whenever for other numbers, you have to write it like what? Norm xp. Norm xp is nothing but pth root of x1 power p plus x2 power p plus etc. xn power p. With respect to this norm also, what? This will become a Banach space, right? And this is called LPN space. This is simply nothing but your Rn and Cn only. Okay, right? Because of this norm, we call this as what? LPN space. This LPN space is also a Banach space. LPN means this p is there, no, underscript. This p is the power, okay, nth root of, like that, sorry, pth root of, okay, pth root of x1 power p plus x2 power p, and this n stands for the number of coordinates here. This is n tuple, no, that is n elements are there, no. So here, if it is r3 means what will you have? lp3. If it is r2 means lp2. If it is Rn means LPN. So the number of coordinates here that comes in the that comes above, and this P stands for the power. Okay, so both are the same space only, but we are defining norm in different ways. Let us see one more way of defining the norm. See here, P be a real number which satisfies the property greater than 1 and less than infinity. Here I am going to take a sequence. In the previous case, I have taken n tuples, no. Here I am taking a sequence. Sequence means x1, x2, etc., xn, etc. It goes up to infinity. So there will be no end. Here, in the collection of sequences, I am defining norm xp as summation n equal to 1 to infinity modulus xn power p the whole power 1 by p. This is also nothing but pth root of x1 power p plus x2 power p plus x3 power p plus etc. plus up to infinity. Only the extension of the above one. What's the difference between the previous norm and this norm? In the previous norm, you are defining in Rn. Rn means what? It will be n tuple. Here you are defining for what? Only R only, but you are considering them as sequences. So sequences means what? It goes up to infinity, infinite sequence. So in that case, the same norm is defined here. Here it runs from 1 to n. Here it runs from 1 to infinity. Okay, this is written as LP space, and this is also a Banach space. Okay, this is LPN and this is what? LP. Why we removed n here? Here it ends up to n. Here it is not ending, so we write it as LP space. Then another way of defining. See, consider the space of all n tuples. The same thing. X is equal to x1, x2, etc. up to xn of scalars. Now, I am defining norm x infinity. From this itself you can understand. Here p means what? Pth root of. But when you have infinity, that there you have to take what? Maximum of mod x1, mod x2. x1, x2 are what? Coordinates of this x. Maximum of mod x1, mod x2, etc. mod xn. This is again a Banach space. And how will you denote it? L infinity n. Why you put infinity here? Because you are taking the maximum value. Okay, no root is taken here, so it is L infinity, and here yn because you are talking about n tuples, so L infinity n. This is also a Banach space, right? And this can be written as, that is norm x infinity is equal to limit norm xp as p tends to infinity. Okay, right. Then another one is L infinity space. This is L infinity n. Next one is L infinity alone. So can you guess what it will be? Here it ends up to n, no? There it will go on. That means what? It's a sequence. So in sequence, how will you define? Sequence, when you this maximum function has to be replaced by supremum. Only for finite number of entities, you have to use maximum function. When you have infinite number of entities, you have to replace that maximum by what? Supremum. Okay, this is for finite case. Maximum means for finite case. Supremum means what? For infinite case. So norm x is equal to supremum of the coordinates. Among all the coordinates, which will be the supremum. That is called the norm, and this Banach space is denoted by L infinity. So how many Banach spaces we have defined here? LPN. Okay, both P and N are finite numbers. Next one is what? LP. LP means P is finite. So here it's a sequence. Next one is what? L. Next one is what? L infinity N. Only N is finite. Here infinite norm. And the next one is L infinity. Both are endless. Right. So different norms we have defined in the same space. Right. Next one. The set C of all convergent sequence in a closed linear subspace of L infinity, and hence it's a Banach space. See, suppose if you take a convergent sequence, it will be what? Closed linear subspace, no? Therefore, it will become a Banach space. Next one, the set C naught, which is a subset of C, the above subset, which consists of all convergent sequence with limit 0, is another Banach space in the same family. Next one, consider script C of x, the set of all bounded continuous scalar valued functions defined on a topological space with norm f is equal to supremum of modulus f of x. This is again a Banach space, and this norm is called what? Uniform norm. So norm f, how do we define? Supremum of f mod f of x. So what are the functions you are taking here? Bounded continuous linear functions. Okay, right? So this will become a Banach space. Then next one, in R2 I am defining different kinds of norm. The first one is R2 means what? Two tuple. X is of the form x1 comma x2. The first norm x1 is defined to be modulus x1 plus modulus x2. This is one norm. The another norm is norm x2. This is what already we have defined in the previous page. It will be what? Square root of modulus x1 square plus modulus x2 square. The next one is norm x infinity. Infinity means what? Maximum of modulus x1 comma modulus x2. Next one is norm xp is equal to pth root of x1 power p plus x2 power p. See, whenever you choose this p has to be greater than 1 and less than infinity. Suppose if you take p less than 1, then the unit sphere, that is set of all x for which norm xp less than or equal to 1. This is a unit sphere, no? This will be convex for p greater than or equal to 1. But for p less than 1, it will be not convex. Okay. And for p less than 1, this will not yield a norm. Okay. So this is an important thing, that is, this LP space you are defining, no, that P has to be greater than 1 and less than infinity. In that case only it will become as a norm. Otherwise it will not give you a norm. So this is a diagrammatic representation of all the norms that I have already defined. See, this is norm x1 equal to 1 is this diamond shape is there, no? That is norm x1 equal to 1. Next one is norm x2 equal to 1. That is given by the circle, unit circle. Next one is norm x infinity equal to 1. That is given by the outermost square. And norm x half equal to 1. That is given like this. Okay, actually this is not a norm because half is there, no? P value is equal to half, that is less than 1. So this will not give you a norm. Just this is a representation of different norms in R2 space. Okay, that's all. Thank you.